In this video, we are going to talk about the Laplace transforms, right? So what does the Laplace transform do? So we are basically having a function, right? A function with respect to time, a function f of t, and we are going to transform it from the time domain, which is the function f of t, into the s domain. This is capital F of s. So this capital F of s is the Laplace transform of the function f of t. So what the Laplace transform does is basically transforming this function f of t in the time domain into the s domain. So I'm going to write down the definition of the Laplace transform of the function f of t, and then we are going to use that to find the Laplace transform of these three functions. So the Laplace transform of a function f of t, this is given as the integral from 0 to infinity of e raised to the power negative st, and this is multiplied by the function that you are seeking to transform f of t, and then dt. So the main idea here is that you are integrating from 0 to infinity, that is always fixed, and you are always integrating in the time domain dt. So this letter here, s, is a constant in the t domain, so we are going to treat all those ones as constants. So in this exercise, what I'm going to do is to find the Laplace transform of these three functions. So the first one is just a constant, which is 1. The second one is an exponential function, which is e raised to the power at, and a polynomial of the nth power. So these are the three functions that I'm going to transform. So when you're transforming a function f of t into the s domain, the Laplace transform of the function f of t is capital F of s. Alright, so let's dive right into finding these Laplace transforms. So the first one is 1, which is a constant. So the Laplace transform of a function, so the function here is 1 for the first one in our table, and this one is equal to the integral from 0 to infinity of e raised to the power negative st, and this is multiplied by 1, and then integrating over the time domain. So the Laplace transform of 1, that is the same as capital F of s, right? So I'm just going to replace this one with the capital F of s as the Laplace transform of 1, and this is equal to the integral from 0 to infinity of e raised to the power negative st, and then dt. So this one is trivial, so we are just going to integrate this. So s here is a constant in the t world, so what I'm going to do is just to differentiate that and divide. That is going to be negative 1 over s, and then e raised to the power negative st, and now take the limits of integration from 0 to infinity. So this is capital F of s as the Laplace transform of the function 1. So f of s is equal to negative 1 over s, and now let's take the limit. So here we are going to take the limit as, let's say, t goes to infinity of e raised to the power negative st. That is the upper limit, minus the lower limit is going to be e raised to the power negative s times 0. Alright, cool. So f of s, this is equal to negative 1 over s, and now as t is approaching infinity, because this one has a negative exponent, as t is approaching infinity, then the whole of this one is going to be approaching 0. So that is going to be 0 minus this exponent here is now 0, and e raised to the power 0 is 1, and that simplifies to positive 1 over s. So when the function is equal to 1, then we are going to have 1 over s as the Laplace transform of the function 1. So the Laplace transform of the function 1 is just equal to 1 over s, which I'll fill in our table. Alright, cool. So the next one is the exponential function e raised to the power at. So that is the same drill, so we just have to replace 1 with e raised to the power at, and that will be the Laplace transform of the function e raised to the power at. So the second one, the Laplace transform of the function e raised to the power at, this is the same as the integral from 0 to infinity of e raised to the power negative st, and now multiplied by the function e raised to the power at dt. So this is the Laplace transform of the function e raised to the power at. So this can be replaced with just f of s, capital F of s, and that is equal to the integral from 0 to infinity of now applying the laws of indices here. This will be e raised to the power, you can factorize negative out, and this will be s minus a times t and then dt. Cool. So now because we are integrating in the time domain, this one is a constant. S minus a is a constant in the time domain, so this is trivial. So capital F of s as the Laplace transform of our function is going to be differentiating this one with respect to time. That is going to be negative into s minus a. So we are going to divide negative 1 all over s minus a, and then we repeat the function e raised to the power negative s minus a t, and now we are done. We put the limits of integration from 0 to infinity. Now let's take the limit, shall we? So f of s is going to be negative 1 all over s minus a, and now the limit. So we are going to take the limit as t approaches infinity of e raised to the power negative s minus a times t, and now the lower limit is going to be minus e raised to the power negative s minus a times 0. This is what we have after plugging in the limits. So f of s is equal to negative 1 over s minus a, right? So here, as t is approaching infinity, here we are imposing the assumption. The assumption that we are imposing here is that s is strictly greater than a, right? So if s is strictly greater than a, it means s minus a is a positive number. So if s minus a is a positive number, that means that this one is going to be approaching infinity as t is approaching infinity. Everything here is going to be approaching infinity, and as that is approaching infinity, everything here is going to be approaching 0 because the exponent is a negative number. So this one will reduce to 0 as t is approaching infinity, conditioned on the fact that s is greater than a. So minus this one here, the exponent here is 0, and now e raised to the power 0 is 1. And this is equals to positive 1 all over s minus a. Yeah, so this one is the Laplace transform of the function e to the at. That is 1 all over s minus a. This is based on the condition that x is strictly greater than a. So this one is the Laplace transform of the exponential function e to the at. So this is 1 all over s minus a, and this is conditioned on the fact that s is strictly greater than a. Cool. Now let's go to the last one, t raised to the power n. Let me switch colors, make things colorful. So we are going to find the Laplace transform of the last one, which is t raised to the power n. So this is the integral from 0 to infinity. This is e raised to the power negative st, and this is multiplied by our function t raised to the power n and then dt. Here we are going to apply integration by parts because we can combine the exponents here. So integration by parts, let's do the di. So d for differentiation and I for integration. I am going to differentiate t raised to the power n. This is plus, next one is negative, and I'm going to integrate e raised to the power negative st. Cool. So now differentiating this one is equal to n t raised to the power n minus 1, and integrating that is going to be negative 1 over s e raised to the power negative st. So what we normally do, we have to multiply diagonal terms. When we do that, we are done with the integration, but when we multiply terms horizontally, there is an integral in the process. Okay, so the Laplace transform of the function, so let me call that capital F of s as we know it now. This is equal to the integral from 0 to infinity of, I'm sorry, we are not going to apply the integration by parts here. I'm sorry for this. So multiplying diagonal terms, that is going to be negative t raised to the power n. This is divided by s, and multiplied by e raised to the power negative st, like this. Here we are done with the integration. We take the limits of integration from 0 to infinity, and now negative, when we multiply them, that becomes positive, because we are multiplying terms horizontally, that is these ones, we have to take the integral. So this is the integral from 0 to infinity of what we have, which is now n over s. This is t raised to the power n minus 1, and then e raised to the power negative st dt. Cool. So I'm going to show you in a moment why these limits will evaluate to 0. So we have negative t raised to the power n, and then e raised to the power negative st over s, the limits of integration from 0 to infinity. This n over s, that is a constant in the t world, so I am going to bring it out of the integral in front here, and then I'll have the integral from 0 to infinity of t raised to the power n minus 1 e raised to the power negative st dt. So now let's evaluate the limits here. So let me do this now. So evaluating the limit, so this negative 1 over s, that is a constant in the t world, then I am going to take the limit as t approaches infinity of t raised to the power n all over e raised to the power st. That is, this st can become a denominator and become a positive e raised to the power st, right? And now minus the lower limit. When you plug in the lower limit, t raised to the powers n, that it goes to 0 as t goes to 0, and then this one goes to 1, and everything goes to 0 for the lower limit, which is 0, like this. And we have plus n over s, and then the integral from 0 to infinity of t raised to the power n minus 1 e raised to the power negative st dt. So by just looking at this one is also the Laplace transform of the function t raised to the power n minus 1. But let's evaluate the limits. Capital F of s is equals to, so here, because when you plug in infinity, we have infinity over infinity, so we have to use the L'Hopital's rule. So negative 1 over s. Using the L'Hopital's rule, it means that the limit as t approaches infinity, we are going to differentiate the numerator, which is t raised to the power n, and then we differentiate the denominator as well, which is e raised to the power st, like this. And then plus n over s, the integral from 0 to infinity of t raised to the power n minus 1 e raised to the power negative st dt. Cool. So when we differentiate this, what do we get? So here, when we differentiate, let's put in a limit here. So the limit as t approaches infinity, differentiating is going to be n times t raised to the power n minus 1. This is what we have. And now the denominator differentiating is going to be se raised to the power st. And we are still taking the limit plus n over s, the integral from 0 to infinity, of t raised to the power n minus 1 e raised to the power negative st dt. Okay, cool. So now this one, when we plug in infinity again for the numerator, that is going to be infinity, and infinity for the denominator, that is going to be infinity, right? So as we keep on differentiating, because we still have infinity over infinity, as we keep on differentiating, this one is going to end up with n factorial, that is this one, right? So the numerator is going to end up with n factorial if we keep on differentiating. We differentiate to the point that the power is now 0. So we are going to get n factorial, which is a finite number, but the denominator is still going to be s raised to the power n times e raised to the power st. So the numerator becomes finite, but the denominator is still infinity. So a finite number over infinity is going to be 0. So the upper limit as t is approaching infinity, this term is going to be approaching 0, right? So f of s here is going to be equal to negative 1 over s, and now this is 0 plus n over s, the integral from 0 to infinity of t raised to the power n minus 1 e raised to the power negative st dt. So this is equals to n over s, the integral from 0 to infinity of t raised to the power n minus 1 e raised to the power negative st dt. Cool. So now what do we do next? F of s is equal to that, so n over s, the integral from 0 to infinity of t raised to the power n minus 1 e raised to the power negative st dt. So we have observed a pattern here. So we see that the Laplace transform of the function t raised to the power n, we have n here which is multiplying in front of the integral, but then the power of t decreases by 1. Let's do it again for the second time, and then we establish a pattern, and then we can write the general solution. Okay, so let's go again with integration by parts. So d for differentiation and I for integration. This is t raised to the power n minus 1. That is what I'm differentiating, and I'm integrating e raised to the power negative st. This is plus, next one is negative. So differentiating, this one is n minus 1 multiplied by t raised to the power n minus 2, and this one is going to be negative 1 over s e raised to the power negative st. Cool. So here when we do this, we have to multiply diagonal terms. We don't have to take the integral, but when we multiply terms horizontally, we take the integral. So the Laplace transform of our function t raised to the power n is n over s in front, and then applying the differentiation integration by parts for the second time, that is going to be negative t raised to the power n minus 1 times e raised to the power negative st. This is divided by s. The limits of integration from 0 to infinity. And now negative, negative, that's positive. So plus the integral from 0 to infinity of n minus 1 t raised to the power n minus 2. And this is multiplied by e raised to the power negative st, and then dt. And this is what we have. Cool. So f of s is going to be equal to, so this one again, the limits will evaluate to 0 from the L'Hopital's rule, right? So this one is going to evaluate to 0 again. So we have done this before, we don't need to do it again. So that is going to be n over s, and now this is 0, and now we are going to multiply that one by this integral, and that integral is going to be n minus 1 over s outside, because they have nothing to do with t. The integral from 0 to infinity of t raised to the power n minus 2 e raised to the power negative st, and then dt. So we have observed this pattern. The pattern is that when we are taking the Laplace transform of this one, the power here will multiply in front, but then the one inside the integral is going to reduce by the power 1. So this one is n minus 1, and the power decreased to n minus 2. So this is what we have. So by just this observation, we can find the Laplace transform of something like t raised to the power n minus 2. So this one is going to be n minus 2 all over s, the integral from 0 to infinity of t raised to the power n minus 3, and then e raised to the power negative st dt. So by just looking at the pattern, we can write the Laplace transform of t raised to the power n minus 2 as this. So in the end, we have f of s, and this is equal to n over s. This is multiplied by n minus 1 over s, right? Excuse me. And this one is going to multiply by this one, which is the same as n minus 2 over s, and this is multiplied by the integral from 0 to infinity of t raised to the power n minus 3 e raised to the power negative st dt. So we can keep doing this using integration by parts. So we continue to do this until the power of n decreases to 0. So we continue doing this until this power runs out to 0, t raised to the power 0, right? So I'm going to write down what will happen at that point when the power decreases to 0. So we are going to have n times n minus 1 times n minus 2, right? All over the s's are s times s times s, and this one is actually going to continue until the power of n decreases to 1, like this. We have 1 over s here, and now we have the integral from 0 to infinity. Because we have 1 here, what is going to be the power of t inside the integral? So the power of t is going to be 0, that is going to be n minus n. So what we have here is always more than the power of t inside the integral. So that is what we have from the pattern. So this one is less than the n minus 2 here, right? So if you have 1 here, that means that the power of t inside the integral is n minus n, which is 0. And this is multiplied by e raised to the power negative st dt. Cool. So we have f of s, and this is equal to, so now we have n multiplied by n minus 1. This is multiplied by n minus 2. This one continues until 1. And then we are going to have s times s times s. And this one continues for s times. Then we are going to have the integral from 0 to infinity of e raised to the power negative st dt, because t raised to the power 0 is 1. So f of s is equal to, this one is familiar, n times n minus 1 times n minus 2 up until 1 is going to be n factorial, divided by, this one is s times s times s multiplying itself n different times. So this is s raised to the power n. And we have the integral from 0 to infinity of e raised to the power negative st dt. We did this when we started by finding the Laplace transform of the constant 1. So this one is just a Laplace transform of the constant 1. So what is the Laplace transform of 1? We can go back to our table and then we find out. So the Laplace transform of 1 is 1 over s. So we are just going down there and we are going to replace that integral with 1 over s, because this integral is the Laplace transform of 1. So f of s is equal to n factorial divided by s raised to the power n times 1 over s. And this is equal to n factorial divided by s raised to the power n plus 1. So when the function is t raised to the power n, the Laplace transform of that function is n factorial divided by s raised to the power n plus 1, like that. So we can now go up and then fill our table. So this is the Laplace transform. So this one is n factorial divided by s raised to the power n plus 1 as the Laplace transform of the function t raised to the power n. So if we have this table and you are given some questions, so let's do an exercise here, a quick one. So the Laplace transform, you are asked to find the Laplace transform of, let's say, e raised to the power 4t, like this. So this one is going to be equal to, so e raised to the power 4t, we are going to use this one. So a here is equal to 4, that is the constant. So the Laplace transform is 1 all over s minus a, but a here is equal to 4. So 1 over s minus 4 is the Laplace transform of e raised to the power 4t. Cool. Now if you are asked to find the Laplace transform, and this one is the same as your f of s in this case. So the Laplace transform of, let's say, the function t raised to the power 5, like this. So this is equals to what? So this one conforms with the final one that we found here, t raised to the power n. But n here, the power is 5. So we just replace 5 here and that will be the Laplace transform. So this one is going to be 5 factorial divided by s raised to the power 5 plus 1, which is 6. So this one is equal to 5 factorial is 120 divided by s raised to the power 6. And this is the same as capital F of s. So the Laplace transform of the function t raised to the power 5 is equal to 120 over s raised to the power 6. So these are the Laplace transforms. So that is how I solved them. So in the next video, I am going to find the Laplace transform of the sine of at and the cosine of bt. So those are the trig functions. So I would ask you to join me in the next video as we derive the formulas for the Laplace transform of the trig functions. And if you enjoyed this video, give me a thumbs up and subscribe to Calculus Diaries, and I will see you in the next one. Bye bye.